Welcome everybody. This is the Icon Book and Paper Group lecture on black and brown inks. Just a few things before we start. First, we will share the recordings and the presentation after the event by email. Second, there will be a short Q&A session at the end of the talk if you have time. So please use the Zoom's Q&A feature to write your questions. Lastly, if you are interested in our events, there will be a 4-day online conference in October. I put the link on the chat board, or please search #IconBPG21. Thank you. Okay, now I'm going to leave you in the very capable hands of Dr. Hannibal. Thank you very much.
Good morning, colleagues in America. Good afternoon, colleagues in Europe, and good evening, colleagues in Australia. I'm glad that I have such a big audience. It's flattering. Well, who am I? On this picture taken from 1988, probably you can spot me, or not, I don't know, because I'm on the right side. Well, I studied chemistry at Utrecht University, and I obtained my PhD at Delft University of Technology with Professor Dr. Herman van Beckum. Although I started with Professor Ton van Beek, unfortunately in 1988 he suddenly passed away, and I had to shift to another group. Because of this, it took somewhat longer to finish my PhD, and I had to look for a job. That's how it goes in the Netherlands. So I got contact with the Royal Library, and I got a job there, temporary, with desk research on mass conservation of book and archival materials. And through this, I came into contact with the Central Research Laboratory for Objects of Art and Science, the predecessor of our institute, the Cultural Heritage Agency of the Netherlands, where I work now. So this I got into the conservation business. This is the way. My talk will be about black versus brown inks used for writing and drawing. And I will start with something about the history of black inks and how to know what kind of ink you have, identification, something about chemistry, and something about treatment, and specifically the treatment of iron-gall and corrosion. And I will talk a lot about chrome-logwood ink, my most recent topic, which I did research on in relation to Vincent van Gogh's drawings and letters. So this guy, shown on the drawing by Rembrandt, is Willem Bartelsson Ruiter. And it's a funny thing because this drawing was in the private collection, and the owner from Germany sent it to the Rijksmuseum to be identified, and it was a real Rembrandt drawing. And she sent it in an envelope, just backed it by postal service. What is an ink? Well, the American manufacturer Thaddeus David from New York published a very nice book on the history of ink, including its etymology, chemistry, and bibliography in 1856. And Davis defined an ink as a colored liquid employed in making lines, characters, or figures on surfaces capable of retaining the marks made. It's interesting to know that the word ink in different languages is linked to different functions of ink. So like Italian, inchiostro, is derived from the Latin encaustum, or the Old Greek encain, which means to burn in. And the English word ink, and the Dutch, by the way, say inked, and the French encre, they have the same root. Whereas the German tinte is linked to tinctum, the Latin, which means painted. That's another characteristic of ink. So some inks behave like paint, like soot inks. The modern Greek, however, uses melani, which means dark colored or black. And the Swedish and other Scandinavian languages use the word black, so that's obvious. So interestingly, for most people, ink is linked to black ink because probably black ink was used for writing and drawing already in very early times. So iron-gall ink is typically an ink which burns in because it's applied as a solution partly as a pigment dispersion depending on the oxidation state. And the ink is inside the substrate, like this should be paper, for instance. Then the ink penetrates the substrate, and actually through oxidation, most of the ink is formed. So you can see the ink darken after application, which means that it's very difficult to remove the ink from the substrate. Whereas soot-based inks, they are on the surface, they stay on the surface. So soot-based ink on like a closed surface like papyrus will stay on the surface, and it can relatively easily be removed. Now, a little bit about history, and I won't explain everything because it's too much now. But actually, the oldest text we know is a papyrus found in the tomb of Nefertiti, pharaoh from 25th century before Christ. And it's a soot-based ink with gum arabic probably on papyrus. So when was first iron-gall ink used? Well, we know that iron-gall ink complexes were used for dyeing textile. So it makes sense in Egypt that they used iron-gall ink to mark the laundry. They had central collecting places for washing the laundry. And of course, soot-based ink is not wash resistant. So they should have used another type of ink for marking the laundry. And this very well could be iron-gall ink. And there has been some recent studies showing that indeed this type of ink was iron-gall ink. Philo of Byzantium in the 2nd century before Christ already mentioned the name of a secret ink where you had to write with a nut gall extract and then develop the ink with iron sulfate or vitriol containing iron. So then the writing would appear. Cicero, in the time of Cleopatra, 1st century before Christ, mentions the use of sepia ink. So sepia is from the cuttlefish. That I will explain later. Pliny the Elder, in his Historia Naturalis, describes this similar secret ink as Philo of Byzantium. And Pliny, of course, he was killed by the volcanic eruption of Vesuvius in 79 AD. Now, when was really iron-gall ink become popular as a writing ink? That was, it's believed that's in the 7th century AD. And why is that? Well, there are theories that when the Islamic Arabs conquered Alexandria, and Egypt had a monopoly on the export of papyrus throughout the old world, the antique world, there was no papyrus available anymore in the antique world outside Egypt, and Pergamon became the capital of parchment trade. Parchment already was known long before, of course, but then parchment became the main writing material to write on, main substrate in the antique world. And parchment, of course, is a porous substrate, so it makes sense that then iron-gall ink was used more and more. And later, of course, paper was introduced from China. So it's believed that 105 Cai Lun describes the paper production from mulberry tree in China, and it was taken by the Islamic tribes to the west through Spain in the 12th century, and then paper becomes the main substrate. After Columbus discovered America, he landed on Hispaniola in 1492. there were new sources for black dyes found in Central America, like logwood. And this was brought to Europe by the Spaniards, and I will tell about this later. Now, the 19th century shows a lot of developments. First of all, through the increased schooling, people got schooling, there was an increase in ink demand, and there was a need for industrial ink production. So many ink firms started in the 19th century, like Encre Antoine in Paris, or Gardot, French firm in Lyon, or Gimborn, Dutch firm. That started in 1855 in Germany, by the way. And also Neelmeyer, that was taken over by Talens, well-known firm. So before this industrial area, ink was produced at the pharmacist. You could order it, like this picture shows a typical pharmacy in England. Now, there was another development that the old writing utensils, like the geese feather or feathers of birds, which were used, were not really sufficient enough. So there was the introduction of the steel pen nibs, the stylus. It started in Birmingham around 1830. Now these, you know that iron-gall ink is can be quite acid, and I will talk about that later. And Runge, he was the first to say, well, there should be, you can use another base material like logwood to make a perfect black ink. Now we also know that in this industrial era, synthetic dyes were coming up, one made, like the first one, morphine by Perkin in 1856. But actually Runge was earlier with aniline black already in 1829. But he didn't have the commercial side to have it produced in large amounts and used. Now, when in 1938, the Hungarian brothers Biro patented the ballpoint, this made quite a difference, because after the Second World War, the ballpoint became very popular as a writing utensil, and the fountain pen and the stylus, their need was they were not used as much anymore. Well, actually, I wrote with the stylus, the steel pen nib, at the primary school still to learn how to write properly. But most people use ballpoints or felt tip pens nowadays. Now, we have different types of black to brown inks, like bistre, which is actually the coal tar. So the soluble part of the burnt wood. Whereas Chinese ink, actually, I think the better name would be Egyptian ink, because they were one of the first to use this type of ink, uses the insoluble part combined with gum arabic. So that's pure coal. Sepia is the ink derived from the gland of the cuttlefish, which, if it's agitated, it will produce this substance. It would be interesting to know some recipes for sepia, some historic recipes when real sepia was used. Maybe you can help me with this. The ink, you can also make ink from the spores of the inky cap, and I only have one recipe from a botanic determination book for mushrooms, and it would be nice to have some more recipes and really historic recipes where the ink was used in a document. For iron-gall ink, I will explain later, and also chrome-logwood ink. Those are the organometallic inks which I will deal with later. So all these inks have more or less similar colors. They are black to brown. So how can you distinguish these? there's another thing, because if they are freshly apart, like iron-gall ink, it's black, but if they are aged, they turn brown. So that makes it even more confusing. And these are a series of inks in different ratios, which I'll explain later too. Of course, if you have iron-gall ink corrosion, like this sketching letter by Van Gogh shows, it's obvious that you are dealing with an iron-gall ink. But ideally, you would not like to have to see this happen, of course. It would be dramatic already. Now, first thing you can do, of course, is use a camera and photograph. And if you have an infrared camera, like you see here for photographing this drawing by Van Gogh, Landscape with Hut from Arles, this infrared camera, the reflectance in the infrared region between 700 and 1000 nanometer is transferred into red. So everything which is red is organometallic ink. And for this drawing, which has been analyzed further, it's the chrome-logwood ink, which turns transparent in the near infrared. Whereas everything which is soot-based, like a pencil, here the underdrawing, stays black. So this is the way you can see the underdrawing in pencil. Now, if you take reflectance spectra of a chrome-logwood ink, so that's the blue curve here, and the iron-gall ink, you see they both turn transparent, more reflectant in the near infrared. Between, let's say, 700 and 1000 nanometer, the curve goes up, whereas it's quite low between 400 and 700 nanometer. So optically, visually, these applications look the same. You can't see any difference between these two inks. And you also see there is a slight difference in curve shape, which you can see with pure chrome-logwood ink and pure iron-gall ink. And it sometimes can help to distinguish also. But you have to take care, because there can be other components in these inks, like synthetic dyes, and they will disturb the shape of the curve. Now, how is the spectrum taken? And this is a homemade appliance. So with fiber optics, reflectance spectroscopy, the fiber optics, this fiber optics will project the light of a halogen lamp onto the object, and the reflected light is captured by the second fiber and taken to the spectrometer, and then you can see the spectrum on the computer screen. Now, another way of identifying inks could be the iron test. So if you have a lot of iron in your ink, it could mean that you have an iron-gall ink. But of course, there can be other inks that contain iron, and I will show that later. In some cases, chrome-logwood ink can contain iron, and there are also existing iron-logwood inks, by the way. Commercial test paper, for what you can buy at Merck, was that the compound is water soluble. So if you use this test paper directly on the object, you get the stain. Whereas this is why we developed the test paper with batophenanthrene, which is a larger molecule and not soluble in water anymore. So you can moisten the test paper and then put it on the object without, you have to dip it off on a filter paper before to be sure that there is no moisture coming off anymore, no visible water. And then if you put it on the object for half a minute and there is iron-2 present, this will migrate to your test strip and form the red complex. But of course, iron-2 is different from iron-3. Iron-3 ions are very little soluble in water, so you won't see them. So if you want to detect iron-3, you should apply a reducing agent onto your test paper after you did the test. Another way of identifying inks is using X-ray fluorescence spectrometry. And this is a portable instrument which I use for detecting, for taking the spectra of the inks that Van Gogh used in his drawings, letters, on site at the Van Gogh Museum. How does it work? Well, you bombard your material with X-rays, and these X-rays, they excite electrons inside your atoms, and these electrons are swept out of the atom, and the vacant places are filled in by electrons from higher energy level. So this difference in energy is emitted as fluorescence, and it's very specific for the metals or the elements present in the material. So if we take a spectrum from this drawing by Van Gogh Arms, which he made in 1889 in Saint-Rémy, and I took a spectrum at this position, you can see the spectrum on the right-hand side. What you get is a total spectrum, of course, which includes the ink spectrum and the background spectrum, because X-rays go through the material, completely through the material. If there is a backing cardboard, you will also see the spectrum of the backing cardboard. So that's the blue spectrum. The total, and then you shift to the place just near the ink line where you just measure only the paper. So that would be the red spectrum. See, there is some titanium in the paper or in the background of the backboard. And then you can subtract these two spectra and you are left with the pure spectrum of the ink. And now you can see that the ink itself contains only chromium. By the way, the peaks for rhodium, that's this one, copper and zinc are created by the instrument itself. And you can see they also are not there in the net spectrum of the ink. So this ink is a chrome-logwood ink, because this is the only type of ink containing chromium. Another method would be Raman microscopy. In Raman, you use a laser. In this case, we use a 785 laser to extract your material. You have to take a sample, or you can use a portable instrument, and then you don't have to take a sample. But if you take a sample, you can use the microscope, and it's much more sensitive method. In this way, you excite your material with a laser, and you create vibration transfer. So the molecules get a different vibration mode, and this is what you measure. And it's specifically for compounds, so you can measure molecules, not only elements, but molecules. So you can measure organic dyes and pigments, and inorganic pigments and polymers at the same moment. One of the problems of Raman microscopy is if you have fluorescence in your sample, like fluorescent compounds in your paper, they can overrule the Raman signal, which is quite weak. In this case, there's a trick. You can add a silver or gold colloid to enhance the Raman signal. And for specific molecules like methyl violet, a synthetic dye, it's been shown that one molecule can be detected this way. It's very sensitive. And it works very well for like aromatic compounds, so compounds having conjugated structures in the molecule. Now, I did some investigation with this technique on chrome-logwood ink and iron-gall ink, and I made model inks according to historic recipes, like a document ink by Schlüter-Neumann, iron-gall ink, which is very well known, and it's described also by officials to use for official documents. Sorry, and the chrome-logwood ink, Kaisertinte, which is used as a normal school ink. Around 1900, it was quite popular. And you can see there's quite a difference between these two spectra. So indeed, you can identify chrome-logwood ink and distinguish from iron-gall ink with this technique. Problem is that it's quite difficult to get a good spectrum because it needs, if you add the liquid colloid, you need to follow the drying period and take consecutive spectra and then pick out the best spectrum, because there's one moment that you get a very good spectrum. So I have to do some more investigations on this technique. Of course, you can use chromatography, high performance liquid chromatography, and we have now very sophisticated equipment in our institute using the combination with mass spectrometry. And my colleague Agnes Proanyu-Gaibor, he's the technician and specialist on this. A long time ago in 2002, I already took some samples from an iron-gall ink, and another colleague, Martin van Bommel, did some analysis of the samples. And I took the samples with the magnesium oxide rods. And this is a popular technique nowadays in our institute, how to sample ink from the surface of an object, of a manuscript. And one of the characteristic compounds when you have calotannins, you usually find ellagic acid, and this will show up as a peak in the HPLC chromatogram, as you can see here. And these chromatograms are quite different. Here, the red one is iron-gall ink, 100 times diluted from the other type of black inks like sepia and bistre. And it depends also on the source, from which source you have the bistre, for instance, in this case. So this would be a technique to identify iron-gall ink as well. What are iron-gall inks? They are, well, calotannins. They are derived from the nut galls or bark of oaks. They combine with soluble iron salts, like iron sulfate. This is a picture taken from UNESCO site in Rammelsberg near Goslar, where they show up as stalactites in the mine. And it's very interesting to study how this production took place during the centuries. And you need binding media like gamma arabic. And of course, you need a solvent and transport medium like water. What are nut galls? They are the outgrowth of oak leaves or on the branches also of oaks, and they are caused by the stitch of a gall wasp. And actually, the plant produces the nut gall, and the tannins present are representative of the plant, always representative of the plant. So if you have a nut gall growing on an oak, it's the same calotannins present as in the wood. The gall wasp grows as a small baby inside this nut gall. And in autumn, these nut galls fall with the leaves, and the gall wasp eats its way out. And the best ones were collected just before the hatching of the gall wasp, because they had the highest content of calotannins. So this is another type of nut gall that grows in China on sumac, and it's caused by an aphid. It's caused by an aphid, sorry. And it has, they were very popular in the 19th and still in the 20th century to use for preparing iron-gall ink, because they contain a lot of calotannin. And here you see a table showing percentages of calotannin from different sources, different provenances. And you can see that the Chinese sumac galls, they have up to 78% of calotannin content, and also the calotannin has the highest number of gallic acid groups, because I showed before that it's central skeleton of sugar-like compound, and these calotannins are bound to the central moiety, central glucose moiety, and depending on the type of calotannin, there can be up to 9 gallic acid groups, which can be split off by fermentation through hydrolysis. Now, gamma arabic is actually a polysaccharide containing different elements, different moieties like different types of sugar bound together. It has a very high molecular mass, up to 1 million, and it contains acid groups which can bind potassium, magnesium, and calcium, slightly acid. And it's derived from the acacia senegalensis, which, among other places, grows in Egypt. So this is why probably in Egypt it was used for the first time. Now, iron vitriol, it's a collection of different types of sulfates. So you can find it on the walls of the Rammelsdijk mine near Goslar, where it's formed through oxidation of the sulfides. So iron sulfide, if oxidized, it turns into iron sulfate. And this is done by roasting the sulfides. So they burned, they made fire, they set fire to the walls. And then the sulfide, which is insoluble in water, was converted into sulfate, which is soluble in water. And they put certain places, they put buckets to collect the water dripping from the surface through along the wall, collecting the solutions. And they put these buckets, the contents, in big ponds where they let it evaporate the water, and they hang ropes in it to let the crystals of the different sulfate grow on it. So you can guess that because of the different solubility of these sulfates, you have a follow-up of different crystals on the ropes. So the vitriols obtained from these are not pure. So if you have vitriols which were obtained from a place near Rome, they contain the highest amount of iron sulfate, they were the purest. And this is pure iron sulfate, by the way, and this is the concentration of the Roman vitriol. So it's quite near pure, whereas the Goslar vitriol is quite impure. It contains also copper sulfate, zinc sulfate, manganese, aluminium, and magnesium sulfate. This was from a PhD thesis from Hickel, but I don't know how statistically sound this research was done. Probably, I mean, you collect from different places, you get also different compositions. Now, long time it was looked after balanced iron galling. What is the ideal ratio between iron sulfate and gallic acid? So I did an experiment where I varied the ratio between iron 2 sulfate, hydrated, and gallic acid, pure. So the first one is a kind of pure iron sulfate solution, which is applied to paper by plotting it with a computer plotter. And the last one is a pure gallic acid solution, and in between are the different ratios. So as you can see from this, the ratio, molecular ratio of 1:1 iron sulfate to gallic acid produces the darkest ink. There's one difference with this one because this one was made without gamma arabic. So you see it appears a bit blacker because the gamma arabic creates a denser color. Now, there are also different opinions about what the compound, the complex between iron and the gallic acid is in the ink itself. And Krekel describes in his master's thesis, and is published in the International Journal of Forensic Document Examiners in 1999, that if you have gallic acid, it reacts with iron 2 sulfate to form a very light colored complex iron 2 gallate, and the product will be sulfuric acid. Of course, that's a bad guy because it will remain in the paper. If there's not enough calcium carbonate in the paper, not enough chalk, the paper will be acid in the inked regions. That's one part of the problem. Now, the iron 2 gallate can be oxidized by air, oxygen, to form this type of complex where you can see you have two iron 3 ions, iron 3 oxidation state, bound to two pyrogallate molecules, but also it could be that you still have the carbonic acid group inside. So that would be two gallic acid units. And if the carbonic acid group is split off, that's what Krekel discovered. That would be in the form of carbon dioxide. So the problem is that you have acid catalyzed hydrolysis and iron catalyzed oxidation, which will cause the damage to the paper structure. And this will take place in the amorphous regions where you have like iron-2 ions migrating out of the ink and protons migrating out of the ink, especially when you have changing relative humidity, creating migration. So the end result will be that the paper will become brittle. Of course, you can de-acidify your paper and you can treat the iron ions. This is what we developed here in our institute using phytate. The idea is that the iron ion will cut hydrogen peroxides to form hydroxyl radicals, and the phytate, if you envision iron as being a scissors, is a box which completely packs up the scissors, so it cannot work anymore, cannot do its damage anymore. That's the idea behind. And this is quite contrary to the EDTA. In this case, EDTA, the box is not large enough, so it cannot completely pack the scissors, the iron-2 ions. Now, phytate is a natural product. It's derived from rice, for instance, the outer shell, and it has a physiological function. It protects the nutrients against oxidation. And this is a biblical principle if Jesus says that unless the grain falls into the ground, it cannot germinate. You know that if seeds are found like in tombs and they are kept in a dry condition, they can germinate if you put them in soil. And this is showing that this function works over a long time. Now, this is the structural information about phytate. It's also a kind of central structure, hexahydroxyhexane, completely phosphorized. Well, I can go on because time is lacking otherwise. Now, I did accelerate the aging of mock-up samples made with iron-gall ink, very aggressive ink, put in patterns on paper. And as you can see, if you do not do anything, the reference, to age it at 90 degrees centigrade and 35% relative humidity, within, let's say, 9 days or less, 6 days, the strength is halved. Whereas if you de-acidify using calcium bicarbonate solution, you get some improvement in the end, but in the end, not much. So if you combine the two treatments like magnesium phytate and calcium bicarbonate, or calcium phytate and calcium bicarbonate, you get a good improvement of permanence. Well, these treatments we presented at 14 times at iron-gall ink workshops in the States or in Italy, shown here, in Brazil twice, in Italy, in Sweden, in England, and in France, and also even in Armenia. Now, shifting to Van Gogh's studio practice, which started in 2006. The intention of this project was to study Van Gogh's working practice for painting and drawing. And in our group, we studied the drawings and also some of the letters to compare the inks. And the Van Gogh Museum, together with the Kröller-Müller Museum, has about half of all the drawings known by Van Gogh. As you can see, this is the share in the Netherlands. Sorry, this is the share of the Van Gogh Museum, and this is the share of the Kröller-Müller Museum. So we are actually at the most strategic place to study Van Gogh's drawings. Now, using X-ray fluorescence spectroscopy, which which I described earlier, we found out that for 51 drawings studied, about 24% of the inks, 24% of the drawings had chrome-logwood ink pure. 38% of the drawings studied had chrome-logwood ink, but there was also iron present. And 30% of the drawings had only iron, so that presumably was iron-gall ink. And 8% was studied with a different technique because there were no metals which were indicated of the ink. It was a synthetic dye ink, purple ink containing methyl violet, and it was studied with Raman spectroscopy. So if you look at the provenances, you can see that yellow and green bars are mainly present in Belgium and France, whereas the blue bars are present in the Dutch period. So it looks as if Van Gogh shifted from type of ink when he moved from the Netherlands to Belgium to France in 1885. Now, I have a collection of postcards dating from 1900 about to 1941, and I also studied this collection from different countries. And you can see the postcards from France, there is a strong yellow bar indicative of that this is a chrome-logwood ink, which is polluted or which contains also iron. And the other countries are the USA, but there's only one postcard, Austria, Germany, Luxembourg, Belgium, and the Netherlands. So the Raman analysis, which I did using surface enhanced Raman spectroscopy, confirms that the postcards from France, I studied the 1900 postcard shown on this picture before, which by the way also shows a nice picture of the exhibition in 1900 in Paris, the World Exhibition. And you can see from this spectrum, that's the red spectrum that is really very similar to the spectrum of the reconstructed logwood ink. And you can see this is the reconstruction here of the logwood ink. So it looks purple, but as soon as you write with it on paper, it turns black, especially if the paper has alkali. So logwood, when was it introduced? Well, as a dye for iron-gall ink, it was already introduced before 1900 by Ribeaucourt, because at that moment, when there was pure components like pure iron sulfate and logwood extract, and iron-gall ink and tannins, you have a very light ink, and you have to add some synthetic dye to make the writing visible, or another type of dye. So logwood was already added as an extra dye to make the writing visible. But Runge, leaning on the experience by textile industry, he proposed to use ink based on logwood extract combined with potassium chromate. And this is shown how it forms. So you have hematoxylin, which is oxidized to form hematine. And then, it's quite complicated, but it forms this type of complex. So as you can see, there are 2 chromium ions, and they are chromium 3. So that's the lower oxidation state, bound to 4 hematine molecules. So the ideal composition would be 2 hematine bound to 2 to 1. So this is also confirmed by experiments I did similar to the iron-gall ink to find out what is the ideal composition. If you mix hematine in this ratio with chromium 3, like potassium chromium sulfate, you have the darkest ink you get. Also, if you mix it with potassium chromate. So there is an oxidation step involved in this whole system to form the ink. Hematoxylin is oxidized to form hematine, and then you create, because you have chromium, potassium chromate, this is reduced to form chromium 3 ions, and then the ink itself is formed. And there is no acid produced in this case, because actually there is acid used. You can see there are 10 protons needed, but there are only 6 produced in this whole process. What is logwood? It grows in Mexico, and this is the tree which grows in the mangrove forests at the coast of Mexico. And these are the flowers, and these are the seeds. And if you cut the wood, it turns red. The hardwood turns red when it's exposed to air by the oxidation process, because then hematine is formed, and this is a reddish compound. And logwood is named logwood because it was transported in the shape of logs to Europe. And in French it's called bois de Campeche because it grows mainly in the region of Yucatan, Campeche, along the coast. It was transported to other parts of the Caribbean, like Cuba, Jamaica, and Hispaniola, the island, Dominican Republic, and Haiti nowadays, by the pirates. So when there was 17th century, the Spain was at war with many countries in Western Europe, like England, France, and the Netherlands, the Dutch Republic, Holland. And they discovered, the value of logwood as a source for textile dyes, for black dyeing of textiles, especially wool could be dyed in beautiful black colors. So when it was transported to these islands, like the Caribbean islands, logwood was a textile dye, and you can see the shades you can get with different types of metals, different types of mordants like aluminum sulfate or tin chloride or chromium sulfate or iron sulfate or copper sulfate. You can see that you get very dark colors. And logwood black, as it was called, was very fashionable in Paris around 1888, as you can see from this picture from a publishing company. Now, it was transported to Hispaniola only in 1835, and it became quite popular around 1850 because then the French inventor discovered how to make a beautiful color with tin salts, prune de monsieur, it was called. And then in the 18th century, export from Haiti started. And why I'm mentioning this story, because Haiti then was Saint-Domingue, which was a French colony, was one of the most prosperous colonies of France in the 18th century, when it was main exporting colony for sugar and coffee. Now, inspired by the French Revolution in 1789, which took place in 1789, the slaves, over 500,000 slaves were working on plantations in Saint-Domingue. They revolted against their colonizers, and one of the leaders was Toussaint Louverture. And Haiti became the first colony to become independent of France in 1804. Unfortunately, they couldn't trade anymore. They were boycotted by many countries in the West, like the United States, France. And they had to make a deal with France to be recognized again in 1824 And that cost them a lot of money, 150 million francs, which would be about 19 billion euros nowadays. So in this way, Haiti made itself like a slave of France again. And France could import very cheaply the products from Haiti, amongst others, the logwood. So if you look at the exports of logwood in 1,000 tons per year from 1820 to 1920 for different areas of the Caribbean, different countries, you can see that gradually they start increasing until around 1880. The green bars are Jamaica, which was the main exporting country around this time, but Haiti was very important too. And you can see that Mexico was not that important all the time, although the best logwood came from that place. There was a small increase during the First World War because synthetic dyes couldn't obtain from Germany then, and they replaced logwood gradually for black dyeing of textiles. Now, if you look at the import volumes in France, the UK, and Germany, you can see that France was very important in 1894, had a very high import of logwood, and most of this logwood came from Haiti. Now, what happened in France, or also in other places, the logwood was chipped into small chips, like this picture shows, and of course later it was a steam-driven. This is a steam-driven machine, and very big factories were in Le Havre, for instance, at the French coast. Now, these chips were stacked in barrels like these, and there was steam driven through this, and you got the heated water, the boiling caused the hematine and the hematoxylin to dissolve, and you get the extracts from this exit. So this was one way of getting the extract, where you had steam at 100 degrees centigrade. In some cases, superheated steam was used, and this was called the American method, by the way, while the other one was called the French method. And this way of extracting is described in a treatise of manufacturing inks, of an ink manufacturer, and in this treatise it's mentioned that it was also observed at the French company Encre et Fils, which was founded in 1840 in Paris. Well, if you use these high temperatures, you lose some of your hematine. And one of the treatises mentions that they added other compounds to improve the color. They sometimes added aniline dyes, or chestnut extract, or molasses. And if you know that aniline dyes like methyl violet are very light sensitive, this will be of influence of the light fastness of the ink. And well, I come to that later. Now, Uncle Antoine had a factory in the Marais in Paris, and there is a very nice reproduction of the catalogue of 1901. It's reprinted in the French journal Au Fil de la Plume for collectors of utensils, writing utensils. So that's the Club des collectionneurs d'objets d'écriture, and they have a lot of information on this firm and also on other firms. So this ink was sold in shops like this around 1900s, also near the places where Van Gogh lived, for instance, in 1880 probably. And he could have bought it just around the corner. And when he was looking for a black writing ink, and he didn't know probably what writing ink he bought. He just bought it there, and because this ink was more popular in France than in the Netherlands, so this could be the reason why he used this type of ink for drawing and writing when he was in France. And the ink prices were lower than that. The ink prices for that Antoine Eiffis had in their catalog were lower for chrome-logwood ink than for a comparable bottle of iron-gall ink. So this is the reason why I think that Van Gogh used this type of ink when he was working in France. Now, we got lots of information about inks in this very nice building. It's a 15th century archbishopal palace, and I went there with Birgit Rijsland, my dear colleague, in 2017, and we had a very good time. And you can see this is the interior of this archbishopal palace, which nowadays is the library of Beaux-Arts, Fine Arts, the Bibliothèque Fournet, belonging to the municipality of Paris. This shows the cover of the price list 1893, where we found information about the prices of these inks. Now, to conclude, so writing or drawing in black ink is one of the most durable ways of transferring information to us from the past, and therefore preserving both historic manuscripts and drawings. And I have to remind you that writing developed from drawing originally in old times. It will remain an important mission for future generations and for you as a paper conservator. And if you want to have the complete story behind a manuscript or drawing, you have to look at lots of information from the material itself, which you can obtain by chemistry, of course, the chemical analysis, but also you have to look at the context. It's quite obvious, of course. So what we want to know actually is, what did Van Gogh carry in his bags when he was going in the field to make drawings? And by the way, this painting doesn't exist anymore. It was destroyed by the Allied forces in the Second World War in the bombardment in Magdeburg. Unfortunately, that's one of the disasters of war, one of the less serious disasters if you compare it with loss of lives. Now, future research. As I have told, there is an issue about light sensitivity with logwood inks, and this drawing, which I showed earlier, has there is an image of this drawing in 1928 catalog by de la Faye, which unfortunately is in black and white. But if you look at the black and white image and compare it to the grayscale rendering of the colored image, the photograph was taken in 2007 by my colleague Nico Lingbeek during the studio practice project. You can see there's quite a difference in the contrast. So could this be due to the fading of the aniline dye, which we found, by the way, in another chrome-logwood ink on another drawing by Van Gogh? My colleague Art Proagno found aniline dye present in the logwood ink. So it could be. So the future would be to study the light fastness of these type of logwood inks. And of course, it would be nice if we could get a sample of this typical drawing, because this is even a pure chrome-logwood ink without any iron in it. So how did the iron get in it? Well, this is the thing about the recipe change, because originally the recipe that Runge proposed did not contain any acid. But the problem was that the ink was not very durable in the bottle. The shelf life was not good. So later recipes, they changed the proportion of potassium chromate to logwood extract, which resulted in a precipitation of the complex, and then they had to add hydrochloric acid. So chrome-logwood inks became acid again, which means that still nibs of your pens you start to dissolve. So iron start to appear again in the ink bottles. And if you would use an ink bottle for many times, but after a while, the iron concentration would increase. So probably this could be used to relatively date objects if you have this sequence. So sorry for forgetting about this, but I thought, well, this would be useful information too. And I have to thank you for listening to this talk, and I thank my colleagues from the RC mentioned here. And specifically, I want to mention John Havermans, who unfortunately passed away in 2007, who was an inspiring person by organizing the Metals and Paper network, which, by the way, was followed up by the Metales en el Papel, that's organized by Valeria Orlandini. Okay, I thank you for listening. And I can imagine that there might be some questions.
Thank you very much, Dr. Hanneval. It was a wonderful lecture and very informative. Okay, let's move. Yeah, thank you very much. So let's move on to the Q&A session. So I think we are running out of time, but we've selected the first 3 questions. Okay. So the first one is, okay, I read that logwood was sometimes added to iron-gall inks. In XRF data, do I need to get a both chrome signal and no iron signal in order to conclude it is logwood and not a mixture?
Okay, logwood added to iron-gall inks, or you could also have iron-logwood inks, by the way. It means, I mean, let's pose it the other way around. If you find chromium, you can be quite sure that's chrome-logwood, because chromium was only used in combination with logwood. If you find iron, you cannot say, you can say it's not. It could be an iron-gall ink, or it could be an iron-logwood ink. Especially if you nowadays, if you buy a bottle of logwood ink, mostly it's iron-logwood ink, because use of chromium is prohibited. So only chromium will identify that you have a chromium logwood ink.
Okay, thank you very much.
Yeah.
Yeah, thank you. Okay, the second question is, okay, do chrome-logwood inks remain black over time on acidic paper, or do they turn brown like iron-gall inks?
Okay, that's a question. Good question. I did aging of chrome hematine ink, and they turn brown, but that's thermal aging. So we have to do a lot of more study on the properties of these inks. But the point is that depending on how much oxidation takes place, I mean, hematine can be oxidized further, and then you have brown products. So the idea is that you have this chromium complex with hematine, which is violet, dark violet. It's similar to iron-gall ink complex. It's also dark violet. In the ink, if you take the natural products, there are yellow, brownish substances like tannins or whatever. And together with violet, they cause the black. So it's complementary colors, which will give you an impression of black. So if something happens, if it ages, the amount of yellowish brown products will increase, and the amount of the violet complex will decrease. So probably all these inks turn brown in the long term. That's also what we see actually during natural aging. Although the inks I see on the postcards, they still look quite black, and they are over 100 years old. So it could be that light will be a very important agent too for aging. Yeah.
Yes, Thank you very much. Okay, the third question. What is the benefit in using magnesium-based deacidification instead of calcium carbonate as part of the phytate treatment?
Yeah, I expected this question. Let's say if you use magnesium bicarbonate for deacidification purposes, that's a whole discussion. Okay, and I did trials on non-sized paper. So in principle, the product will be basic magnesium carbonate oxide, which is a very high pH. And this is dangerous to the ink also. It will cause discoloration of iron-gall inks and probably also different type of inks, other inks, because it will destroy the complexes. So, but there is discussion is whether this will happen if you have sized paper when there is a sizing agent. So this is why we shifted to pure calcium salts like calcium phytate and calcium bicarbonate in the past. But if you use magnesium phytate in combination with calcium bicarbonate, you don't have these high pH levels.
Okay, thank you very much. I think we got the last question. Okay, about the Raman SERS, S-E-R-S, is it a destructive technique? How do you prepare a sample?
Okay, I take a sample like one paper fiber with some ink. I put it on a microscopic glass plate, and ideally I use aluminium foil, so self-adhesive aluminium foil underneath as a reflecting. So you create a mirror, put it on this mirror, and I add the silver colloid liquid, quite concentrated, and then I do the analysis. I put it under the microscope and do the Raman analysis, and I consecutively take Raman spectra, because during the drying, the contact gets better between the paper fiber surface, the ink, and the colloid. And there is a point that you have a very good signal. But this is the tricky thing, of course, because how reproducible is this technique? Okay, in the future, well, if you have the sample, in principle, you still can use it for different purposes. So in principle, you could use it for HPLC analysis, because then you dissolve your ink compound and you do the analysis. And probably the silver colloid will not disturb anything, because it will remain back. But in the future, we're getting a better Raman equipment, and our Raman equipment is quite old already, 10 years old, and we get a new Raman microscope. And I already had some samples analyzed without SERS, direct Raman analysis, and it worked well. So probably we can directly analyze the ink without doing this. But we have to wait until next year, probably, till we have the equipment.
I see.
But I know from my colleague, Sylvia Centeno, she did analysis of logwood inks already. She published on this. And she didn't use any SERS.
Okay. We look forward to it. Okay, thank you very much. So that's the end of lecture today. Unfortunately, we ran out of time and we can't answer all the questions, but I've put some, I've put Han Neval's email address on the chat board. Okay. So everybody feel free to send questions to Han. Yeah, is it okay? Yeah. And also, again, I'm going to send the lecture recordings and the presentation after the event. So yes, if somebody missed the first part, yes, you can catch up. Okay, thank you very much, everyone, for coming from all over the world.
Wow, yeah.
Okay, thank you very much, Dr. Han Neval, again. Thank you.
Oh, this is the advantage of doing it virtually, of course. Yeah, although I really prefer physics, to teach physically, to teach in face to face.
Yeah,
Yeah.
great. Thank you very much.